Okay, last unit number, whatever we're on, 15. And again, it's a long unit by like calendar days because we don't test until, most of you will be testing on May 16th. That's when the juniors will test. So that's like 2+ weeks away. But the notes packet, there's only 3 days of notes. For a couple reasons. One, like content related, is we just need to continue to practice derivatives. So a lot of it is like embedded derivative practice. But a coordinating or a co-reason would be it's AP test week next week, and we know a bunch of you guys will be in and out for various things, and so because of that, we basically dial it back because we don't want you doing an hour of pre-cal homework every night when you have an AP test the next day. Again, it feels like it's a long unit in some ways, but it's really not a dense unit. It's a very spread out unit because of AP test weeks, and we want you focused on AP test. So that's sort of the big picture reason why there's 3 days of notes for 2 weeks of stuff. Not that you would complain, just offering the explanation. Okay, so in this, today we'll do logarithmic functions, Friday we'll do exponential functions, and then that's kind of it. There's one more day, L'Hopital's rule, but L'Hopital's rule is easy and people like that. Okay, log functions. Trig functions, inverse trig functions are called transcendental functions as opposed to algebraic functions. Exactly what that name means, I honestly don't really know. It doesn't affect what we're doing. You could just say that they're a lot harder functions. How about that? Sounds harder, transcendental. Let's review some algebra properties, some log properties. Natural log is a log of base. What's the base of a natural log? E. Log base E. Do you remember if you have natural log of x times y, what you can do to split that up? Expanding logs. Natural log of x plus natural log of y. Use this one a lot for taking derivatives because it's a whole lot easier to take 2 easy derivatives rather than 1 hard derivative. So peeking ahead, we'll use this one a lot to break up a difficult natural log into 2 easier natural logs, and that makes their derivatives a lot easier. How about natural log of e? What's that equal to? 1. And then while we're here, what's the natural log of 1? Remember, that means e to what equals 1? 0. Natural log of x over y. Right, it's kind of a matching property of that first one. Another one that helps us avoid the quotient rule. Like if we take the derivative of the natural log of a quotient, the quotient rule awaits us. If we use log properties to fix it, then we don't have to use the quotient rule. What about the a out front? Do you remember where that can go? Exponent. So that's another one where we can simplify our derivative process. Although it's written a little bit weird, I think. The arrows is how we use them to make derivatives easier. So we want to split them up because that makes derivative easier. If we take that a out front, that makes the derivative easier. So my little red arrows is the way to use them. You can use them either direction, but the red arrows make derivatives easier. A little side note here: you can't distribute logs. That doesn't work either way. Like, don't do that. But people get confused when they see this stuff. They start doing that kind of thing. Domain of natural log of x? Maybe the graph of natural log of x would be easier if we remember what it looks like. We got some values. Natural log of 1 is 0. Natural log of e, which is like 2.7, is 1. And that's only 2 points. Maybe you remember vaguely what the graph looks like. I like to do the graph first because then it's easy to see that the domain is 0 to infinity. And don't include 0. Another way to say that is you can't take the log of a negative number. You've got to plug in something that's positive. All right, with the picture, we can answer these questions. As x approaches 0 from the right, what's the function doing? As x approaches 0 from the right, the graph is headed down to infinity. 0 from the right, that would be down, down, down we go. How about on the kind of the other end of the graph? As x approaches infinity, what's f doing? It's headed to infinity. Kind of slowly, like relative to a lot of the other graphs that are concave up, that approach it more quickly. This one approaches it more slowly, but it's headed that way. Related to that first limit, vertical asymptote at, but you can't just say 0. X equals 0. Sort of that barrier because you can't log a negative number. Okay, all of that stuff we already know. I mean, in theory, we already know or have seen that before. Now let's figure out what the derivative of natural log is. And we can use our calculator, kind of like we did with sines and cosines, to maybe figure out what it is based on the graph. So grab a calculator. Oh, in fact, looks like that's what someone was doing with this one. So for y1, let's go natural log of x. Maybe graph it, see what it looks like. It's not a great picture. Zoom 4. There we go. That's a good picture. So let's all get to that spot, and then we'll go on from there. But get to that spot on the graph, or on your calculator. Go Zoom 4, and it will pick something that works for you. Okay, everybody got that far? Anybody not got that far? Okay, for y2, we want to graph the derivative of natural log. So that's math 8 is the derivative thing. So derivative with respect to x. We could put natural log in there, or you can put y1 in there, either one. And evaluate that at x. That way, it's going to calculate a derivative for each spot. This is going to take it a little bit of time.
Wait, where do you get y1 from?
Bars. It gives me the y1. And they're on the bottom half of that front page. I think I'm going to turn off the first graph so I don't get confused, like it only shows me one. So I'm not going to look at the natural log anymore. I'm going to look at the derivative of natural log. Does that look familiar? It should. It looks like 1 over x. but we should probably do some things to make sure that it's 1 over x. So let's go trace, and let's put in x equals 1. And again, the calculator does stuff numerically, so 1 over x would be exactly 1. The calculator is getting 1.000003, pretty close to 1. Let's try x equals 2. Yep, that's 1/2.
How do you turn off one of the y's?
If you want to turn off one of the y's, you highlight the equal sign and press enter. Or you can go to the line and press enter and make one of them bold. That way, if you wanted to see both of them, my bold one is the derivative. So I think you're right. I think it is 1 over x. So the derivative of natural log of x is 1 over x. And the derivative of natural log of u, this would be using the chain rule. So 1 over u, but then the chain rule would be multiplied by the derivative of u. If you want to spell it out in words, or at least see it in words maybe, it's 1 over the argument times the derivative of the argument. And that derivative of the argument is the chain rule coming into effect there. Okay, so that's the main rule. There's an alternate rule coming up. 1 over x, or maybe a better way to say it is 1 over the argument times the derivative of the argument. So most of the time it's not going to just be x, because then all the problems would be exactly the same. U is going to be some function that forces us to do the chain rule. Okay, well, what if our base is not e? Okay, property of log. Well, let's fill in the ones we know. Sorry, in the box here. The derivative of natural log x is 1 over x. Derivative of natural log of u is 1 over u times u prime. That we know. Okay, this property of logs, I don't know if you remember this or not, but you can rewrite logs with different properties. The log base b of x is the same thing as natural log of x over natural log of b. That's super convenient if your calculator only has a natural log button, or doesn't have a log base, 3 or 5 or 7 button. You can always convert. Well, natural log of b, that's just a constant. So you could almost view it as natural log of b out front times natural log of x. So 1 over natural log b looks weird, but it's just a constant. It's 3 or 7 or 2.64. Who knows? So if we took the derivative of that, it would be 1 over natural log of b, because there's our constant that's out front, times the derivative of natural log of x, which is 1 over x. I'm going to just leave it like that. So 1 over natural log b, that's from the change of base formula, and then the derivative is 1 over x. So the derivative is still kind of the same, but there's that natural log b there when our base isn't e. All right. So put them both together on this u. We'll have 1 over natural log b out front, 1 over the argument, times the derivative of the argument. So that 1 over natural log b, that's a constant. 1 over u, that's that's the rule for natural log, and then U prime is the chain rule. So there's a lot of pieces to that. Multiple stars on that because you got to know that. Now, for better or worse, all you really have to know is this last one, because that covers all the previous ones. So it's not 4 different formulas to memorize. The better way to think of it is, if you know the last one, it takes care of all the others. Using the chain rule. Well, that's the one we just did. Okay, some examples. Find the instantaneous rate of change. That, of course, is the derivative of natural log of that thing when x equals 2. Okay, so find the derivative, plug in 2. The derivative is 1 over the argument times the derivative of the argument. So that would be 6x minus 4. 1 over the argument times the derivative of the argument. And since it says at x equals 2, that means we'll need to evaluate that at x equals 2. And since we're doing calculus now, that's a safe stop. As weird as that looks, that's a safe stop. In pre-cal, that's not a safe stop. And I don't remember if any of y'all are signed up for the pre-cal AP exam. Any of y'all do that? Well, that would not be acceptable in pre-cal, so you'd have to finish it out. 12 minus 4 is 8.
I heard colleges don't accept the pre-calculus AP exam. Like, there is no pre-calculus class in college. It's really weird.
Okay, so we're finishing simplifying this. 12 minus 8 is 4. 4 minus 1 is 3. So there's my best multiple choice answer. So I'm good with the safe stop, but if it's multiple choice test, we're going to expect you to use your algebra to get all the way there. Number 2, natural log of the cube root. This could be ugly, but there's an algebra trick first that would make our lives a lot easier. What's another way to write the cube root? What power means the same thing as a cube root? The 1/3. So if I stop there, I've got to do 1 over this ugly thing and then the derivative of that ugly thing. But there's kind of a cheat code here. What can we do with the 1/3? Put it in front, and this problem just got a whole lot easier. Whoops, I'm not even deriving yet. I'm still doing algebra. 1/3 natural log x cubed minus 3x. Now we can take a derivative, a much easier derivative. So we'll leave the 1/3 out front. 1 over the argument. So again, don't change the argument. Right? Chain rule. 1 layer at a time. So 1 over the argument. Then chain that to the derivative of the argument. 3x squared minus 3. And that's a perfectly good answer. Multiple choice is probably going to, let's see, what can we do to clean that up? Oh, the 3's could factor out a 3 and cancel it, so x squared minus 1 over x cubed minus 3x. That's your best multiple choice answer. But there's nothing wrong with this as a safe stop, as a free response answer. 3. Natural log of 2x over x plus 3. So if I don't do algebra, then I've got to do 1 over this times the derivative of that. What would it take to do the derivative of... Oh, yeah, you're jumping ahead of me here. What would it take to find just the derivative of the inside stuff?
A lot.
A lot. What's the name of the rule? Quotient rule. Well, we don't want to do that, though. So, yes, Cade, let's split that up. Let's use our algebra properties to make our life a whole lot easier. So now instead of 1 over and making a complex fraction with the quotient rule, now we've got 2 easy problems to do. So 1 over 2x times 2 for the chain rule, minus 1 over x plus 3 times 1 for the chain rule. Let's see, the 2's will cancel. And that doesn't look like any of my answer choices. I mean, I guess it's kind of close, but what do I need to do in order to make it look like one of my choices? Common denominator. So x plus 3 minus x over x times x plus 3. Let's see. Oh, the x minus x goes away. So I'm left with b. That looks terrible. Natural log of the secant of x. Well, let's just apply the rule. 1 over the argument times the derivative of the argument. But you guys are trig calculus experts. What's the derivative of secant? There we go. Secant tangent. Oh, well that was a nice problem then. The secant's canceled. And we're left with tangent. What looked like to be the worst problem turned out to be one of the easier problems. Certainly on the algebra front. Number 5, find the slope of the tangent line. So that's another derivative. Oh, but we got base 7. I don't think I can do anything with the inside, so f prime equals, so 2 goes along for the ride. The change of base means I've got 1 over natural log 7 out front. And then now I can work on the derivative of a log function. 1 over the argument times the derivative of the argument. 15x to the 4th. That's a safe stop. Like it's all there and it's all right. But there's some algebra to go here. Thank you. Let's see. How many algebra steps can we do at once here? 15 over 3 is 5. Times 2 is 10. Nothing's going to mess with the natural log 7 in the bottom, so that can just stay there. And then x to the 4th over x to the 5th is an x in the bottom. I don't want to put that at the end because then it looks like natural log of 7x, and I don't want that. So I'm going to put that x out front like that. And there's our, probably what shows up as a multiple choice answer. Ooh, number 6. What's going on number 6? What rule will we need? McKenna, it's the same one you ask about. Is that 15, 21? I don't know which one on the test that used the... What rule am I going to need? The product rule. I'll need the chain rule as well, but I'm going to need the product rule. And this looks a little crazy, so I think I'm going to kind of slow down on this product rule. Label things, find the pieces, put it back together. Like, you know, if you're confident, you can product rule on the fly, but first product rule with logs, may be best to slow this thing down. So f prime is 3, that's easy. G prime, yuck. It's 5, so I need 1 over natural log 5. And the argument is in the bottom. And the derivative of the argument is in the top. Okay, but I'm not done. Now I got to put all the pieces together, product rule style. So 1 times the derivative of the other. So I'll do f times g prime and see if I can put this stuff together on the fly here. 3x times 2x would be 6x squared. I should better illustrate what I'm doing here. So f times g prime would be 6x squared in the top, and in the bottom, natural log 5 times x squared plus 7. So there's fg prime. Plus the other way around. Oh, this is an easy one because I'll just stick a 3 on there. 3 log base 5 of x squared plus 7. I don't think there's anything we could do with that in terms of like terms or simplifying. So we're starting to really put these things together now. Product rule, chain rule, log rule, power rule, and then a little bit of algebra at the end. Oh man, number 7. What are we doing here? That looks terrible. If we don't do algebra on that, then we're going to be... It's not going to work. But the algebra rule is I can split these pieces up. So 3 times natural log of x plus natural log of square root of x minus 3 minus natural log of the cosine of x. Oh, there's one more thing I can do algebra-wise before I even take a derivative. Oops, I keep putting prime when I don't mean prime yet. What's the other algebra thing I can do? Make my life. That square root can become a 1/2. Okay, algebra. We haven't done even done calculus yet. That's still algebra. Now I think I'm ready to take a derivative. Just leave the 3 out front, and then take the derivative of the pieces. Right? This is the nice thing because you can add derivatives. You can't multiply and divide derivatives. So we used an algebra property to break it up. Now we can just go piece by piece here. Chain rule gets me that 2x in the top. Let's see, so cosine in the bottom. Derivative of cosine in the top. What's the derivative of cosine? Negative sine. And that's a perfectly acceptable safe stop right there. There's a little bit of algebra you could do to clean that up, but we wanted to be fancy, we could say 1 over x, and then cancel the 2's, and then negative negative makes plus, and what's sine over cosine? Tangent. So it's like, you leave it like that if you can, but if it's multiple choice, they might have cleaned some things up for you. Question? I've just left it out front from the very beginning and didn't do anything with it. You could distribute it. I mean, you could get a common denominator. There's some other things you could do, but nah. We did the calculus. There's more algebra. That's for algebra. Number 8 and last, combination of a graph and an equation. My goodness, this looks terrible. Natural log of g over f. So if we don't do algebra, we got to do 1 over g over f, and then we have to do the quotient rule of g over f. Ugh, let's don't do that. Natural log of g minus natural log of f. Much better. So h prime is 1 over g of x times the derivative of g, so g prime of x, minus f of x in the bottom, and then f prime in the top from the chain rule. So at 1 means I need to plug 1 in everywhere. I don't really want to write of 1 4 different times, so I'll just say all of that at 1. G prime at 1. G prime at 1. What's G prime at 1? Good, negative 1/2. So that just means the slope of G at 1 is negative 1/2. G of 1 is 1.5 or 3/2. Ugh, fractions and fractions. That's okay, we can do that. Minus f prime at 1 is negative 1. And f of 1 is 6. Yes, that's a safe stop. Negative 1/2 times 2/3 would be negative 1/3 plus 1/6. Let's see, so that is negative 2/6 plus 1/6 equals negative 1/6. That problem definitely gets the stamp, because there's going to be people who do the calculus right and then mess up the algebra from there, but we got negative 1/6. Again, I wear out that stamp in calculus class because students get the calculus right and then mess it up from there, and then I get to stamp their paper and they laugh because what's the other option? I guess crying. Alright, the worksheet today is worksheet 1. Again, we're getting there in terms of end of school year.